Good afternoon, everyone, and thank you for joining us. My name is Katie Rowley. I'm with the NOAA Central Library and will be the webinar host today. If you are having any issues with audio or seeing the slides, please try logging out and logging back in. That solves most issues. If that doesn't solve it, please chat at me or email library.brownbag@noaa.gov, and I will do my best to troubleshoot that for you. We have a great presentation today. You can ask questions, but we will be holding those questions until the end of the presentation. There is a question panel / chat panel that you should all see. And you are all muted, just to let you know. We will be recording this as well. So if you have a colleague who would like to attend but can't, please point them to the library's either Brown Bag page or our YouTube channel for the recording of this presentation. And with that, I'm going to turn it over to our presenters.
Thank you so much. Good afternoon or good morning, depending upon your time zone. My name is Gina Esco. I'm the Social Science Program Manager in the the Weather Program Office. Our name changed recently and I'm still getting used to it. I have the privilege today of introducing our speakers, but I wanted to give just a short bit of background. As some of you may know, the Weather Research and Forecast Innovation Act of 2017 calls for the creation of a Tornado Warning Improvement and Extension Program. We like to call it TWIEP. TWIEP has since been defined to include two key features: the development of explicit estimates of tornado likelihood and the extension of such guidance into a 1-hour lead time frame. And what's so wonderful about the study you're going to hear today is it's estimating some of the potential economic benefits of such a program for the United States, including specifically for US businesses and for tornado vulnerable populations. So it is my distinct privilege to introduce the PIs, Dr. Kim Klockow-McClain from CIMMS, a research scientist there and one of the lead PIs here, and Dr. Kevin Simmons from Austin College, a professor of economics. Kim and Kevin, the floor is yours.
Thank you. Well, first I want to thank the people at NOAA for giving us the opportunity to conduct this research. And I especially want to thank Harold Brooks and the Severe Storms Lab for their help. As Gina said, my name is Kevin Simmons and I am a professor of economics at Austin College. Before we get started, I just want to also note that Austin College has had a partnership with CIMMS and the Severe Storms Lab for several years. It's one that we greatly value. It's truly a joy to work with the folks at CIMMS and at the lab. Now, Kim is going to discuss the overall project, which includes not only the work of my students, but also includes the work of our postdoc, Alex Ugaroff. The results we're going to share today comes from work conducted by two Austin College students, Allison Beamer and Seth Howard, both under my supervision. In year one, Allison developed and implemented a survey that we believe is the first of its kind. The goal was to ascertain how firm behavior may change if given probabilities rather than a deterministic warning of an approaching tornado. She used firms in our local area, which is north of Dallas, for the focus group, then distributed the survey through chambers of commerce in and near the Dallas-Fort Worth Metroplex. In year two, Seth Howard took the results of that survey and conducted statistical analysis on the behavior of the firms and then the economic implications of their actions. So I'm going to pass it over to Kim, who will now provide a broader overview of the project, followed by Seth, who will then summarize our results. But before I leave, let me once again thank you for the opportunity to present our results to you today.
All right, thank you so much, everybody. Seth, if you could advance one slide, I'll go ahead and get into some of the background. I'm glad that Gina gave a general overview of the background for this research. Our project really is motivated by the Weather Research and Forecasting Innovation Act of 2017. For those who are maybe less familiar with it, I know the weather side of the House is certainly getting to be quite familiar with this bill, but this was a very important piece of legislation that it was the first time in many years Congress had given this much direction in matters pertaining to weather research and weather forecasting. So a number of different kinds of programs and issues were covered in the bill, but one of them was on tornado warning improvement. And this is section 103. I've highlighted the language here on the slide. The Tornado Warning Improvement Extension Program, or TWIEP, as Gina highlighted, and we'll call it that through the rest of the presentation, had two major goals. One, to reduce the loss of life, and two, to reduce economic losses from tornadoes. And our research will touch on both of these in different ways, both of these goals. Now, the way that it prescribes that this be done is by developing more accurate, effective, and timely tornado forecasts and predictions and warnings, including predictions of tornadoes beyond 1 hour in advance. Next, please. So I want to show you what the TWIEP could look like in practice, what some prototypes are looking like, and describe for you what the consequences of that may be for decision makers. But before I do that, I want to describe a little bit more some of the features of the current warning system so you can get a really good sense for what these changes might mean. You can put yourself into the shoes of a decision maker pretty easily, I think, when you hear about the potential changes. So what you see on the left side of your screen now is just the current deterministic warning system. So there are two major aspects of the warning system I want to cover. One is that warnings are, as I just said, deterministic. That means that they are a yes-no type of forecast. And so when forecasters issue these warnings, they may, underneath the surface, have different degrees of confidence that there may or may not be a tornado, but they don't have any really great mechanisms right now for revealing the different feelings they might have about just how likely it is that a tornado exists. The other feature of the deterministic warning system that we work with today is that it's a warn on detection paradigm. So by that, I mean that forecasters wait until there's a sufficient amount of evidence that there is either a tornado now or one may soon occur to issue a tornado warning. And with this, there may be some limits to how long the lead times may be that we achieve in a system like that. We've had lead times that have been fairly stable for many years, averaging about 15 minutes. So that will compare really interestingly, I think, when you look at what the future might look like with TWIEP. Could you click ahead one, please, Seth? So this is an early prototype that describes a little bit what a TWIEP system might look like. It has two important features to it. One is that we might transcend this deterministic just yes-no forecast and actually offer explicit estimates of probability downstream of a storm. This can give then the forecaster the chance to try to describe just how sure they are that a tornado might exist or might not exist. The other thing this frees us to do is lift ourselves out of the warn on detection paradigm and offer some kind of guidance. It might not be that the warning is an hour long, but it could be some guidance that extends out ahead of the warning somewhat to offer something to people who want to make decisions in that time frame so they know that there might be a storm heading their way that could produce a tornado. And this could really radically shape the landscape of the decisions that people make with this information, giving them that much more time, up to an hour or even more. Click again. So a really interesting thing that our work grapples with then, we're interested in understanding how the business or how economic consequences might change, and maybe what the proposition for loss of life could look like if things could get better there. Both of those kinds of studies are working with the idea that we would evaluate the potential effects of a system and system change before we make changes to that system. So this is a key question for us. How do you do that? We decided in this work that we were going to do it in different ways based on different population segments that have very different kinds of decision needs and in ways of framing the choices that they're making. Next, please. So one key population that we were interested in looking at is vulnerable populations. And by this, I mean populations that are more likely to suffer the deleterious consequences of tornadoes when they occur. So these are populations that are more likely, when exposed to a tornado, to experience injury or death, for example. So we're building on work that Kevin did years ago with colleague Dan Sutter, and what some other folks have been doing for the past several years to try to document what are those vulnerable populations? Who is it that particularly is more likely to suffer in the face of a tornado? And there have been many populations that have been identified as particularly in this position. One is individuals living in mobile and manufactured housing. For these individuals, research has demonstrated that fatality rates when they're exposed to tornadoes may actually be somewhat similar to before there was a warning system to begin with. And this is somewhat disheartening news, but maybe not entirely surprising when you consider that the warn-on detection paradigm offers perhaps not a lot of time for those individuals to flee those structures that are insufficient in the face of many tornadoes. And when you think about the lead times being 15 minutes, these people might then really benefit from TWIEP information, having some kind of forecast that falls in a time scale between a watch, which is just much too large for most people to take some kind of preparatory action to evacuate, especially. It's just very, very, it can be hours ahead of time, and it can be most of a state in size and scale. So something between that and a warning that's 15 minutes could be enormously beneficial to those individuals. Another population segment that is more vulnerable to tornadoes is non-native English speakers, and for them, having just receiving the warnings, understanding them can be significant barriers. So having more time may also help improve those processes, get them the time that they need to receive the information through their social networks, through the other kinds of distribution channels they would receive it, and to understand it and to know what it is that they ought to do as a response. So this is the part of the research that we're still doing. This is what my postdoc at CIMMS and NSSL is focusing on. We're about to distribute a nationwide survey that tries to understand the behaviors of these population segments. We've identified at least 4 very key vulnerable populations of interest, and we're going to look at how they make decisions with TWIEP information and compare that to how they make decisions today, and try to uncover, do we see a higher propensity to be able to flee, to get safer? And when we couple this with vulnerability models, we'll be able to create estimates of the number of lives potentially saved. Next, please. So the rest of the presentation today, we're going to focus on the portion of the work that's been completed. This is looking at business decisions. Now, businesses as a population segment are going to be very different from vulnerable populations, so we'll do the analysis quite differently for them. For example, their decisions are more explicitly financial, whereas for the general population overall, we're used to thinking safety first, and we're very much focused on helping people to prevent loss of life. For businesses, there actually are trade-offs to them making response decisions that aren't just about safety, but they're also about financial stake in the outcome. And in this, one kind of concern that could arise is that false alarms, if you have a tornado warning and don't actually incur a tornado, but you've tried to take some protective action, that could carry some cost for you. This is something that we were interested in exploring and has shown up for other kinds of related businesses. Click ahead, please. So there was a recent Freakonomics podcast that actually talked about false alarms, and there was a representative from the SIAC security company that noted that this is actually their #1 priority. It's the one issue they've decided has to be addressed. That false alarms can carry all kinds of costs for both financial issues, but also in trust in the products and services that are provided. So this is something that we thought might very much be the case potentially for businesses trying to respond to tornado threats as well. Click ahead. So false alarms are one kind of outcome that a business could experience, but it's not the only one. So to try to dig into the financial world of what businesses are facing, I put forward here a 2x2 contingency table that can give you a general idea of the kinds of outcomes that might be experienced by businesses, depending on 2 factors. 1, what happens? So was there a tornado or wasn't there a tornado? And 2, what did businesses do in response? Did they take a protective action or did they not choose to protect? And if you look at the left column here, if they do choose to take a protective action, we see that they will incur that opportunity cost for response. So those costs will include things like foregone sales for the time that they are sheltering their employees or patrons, shutting down perhaps manufacturing, production activities could also be included in that. That will all get wrapped up into that opportunity cost C. Now, another outcome that's possible is there could be a tornado and a business hasn't protected. In that case, we would expect them to incur loss L, which we're not taking to be the total losses that could be experienced overall. There's some losses that, you know, if you get hit by a tornado that are not avoidable just by taking a mitigating action. But there is some portion of loss that many businesses can actually try to save themselves from if they do take a protective action, and that's what we take to be L. And then finally, of course, if there's no tornado at their location, they didn't protect, everything's great, no costs or losses. Click ahead, please. So simple decision rule, oh, go back. A simple decision rule that falls from this 2x2 contingency table is that the rational business, and one that has full information, should be expected to take protective mitigating action if the probability of the occurrence of a tornado is greater than the ratio of the cost to losses. In other words, in sort of layman's terms, how much of what they stand to lose if they get hit by a tornado are they willing to put in up front? How much skin are they willing to have in the game to try to save themselves from that loss? You'd expect it to only be a portion of the total losses they might incur is what they're willing to risk. So you're going to get some probability value that's associated with that. In the rest of the analyses that we're going to show you, we'll occasionally show you probability values that you might not think are incredibly high, like 25%. But importantly, if you take a look at the current warning paradigm, we have about 1 out of 4 tornado warnings verified today. So the expected probability, if we were to actually reveal the probabilities under all of our warnings, the expected probability might be around 25%. So as we go along in this analysis, we'll be showing you what businesses do with current information, deterministic information, and take a look at that delta between what they'd prefer to do if they knew the probabilities were that low, something around 25%, versus what they do in deterministic systems today. Click ahead, please. So I'll wrap up and pass things along to Seth just by highlighting our research questions. The first research question pertaining specifically to businesses is, how do businesses respond to weather service warnings now? Interestingly, as Kevin highlighted in his intro, we don't know very much about how businesses respond to the current system. So this isn't talking about any private sector products. A lot of businesses do receive some tailored specific products from the private sector. This is just pertaining to the publicly available information. And we need this information to understand our second question, how might they respond to TWIEP information and compare against a meaningful baseline. We want to understand what might change in the future. So what Seth is going to provide you an overview with first is just, let's talk a little bit about what businesses do. Let's just document what is it that businesses actually do when tornado warnings are issued, and how can we classify those kinds of responses, which of those are cost bearing, and go on from there to question 3. What are the economic implications of changes in business behavior? So we'll show you what the business behaviors are. We'll talk a little bit about the numbers then, just what exactly they're putting up in terms of potential costs and potential losses, and we'll calculate the implications. There's going to be a lot of small calculations you'll see that'll add up by the end. We wanted to show you just the depth of the number of factors that we considered in especially translating our findings from the Dallas metro area to a generalizable sample of businesses across the country, so we can give you just a very simple estimate of what the consequences of TWIEP might be across the whole country for all businesses in a given year. And with that, I'm happy to pass this along to Seth to get into the numbers.
Thank you, Kim. So just starting off, this is kind of our overview. We're really going to go over that survey and behavioral ranking scale at the beginning, and then use those results, go into some descriptive statistics, and then our further analysis. And after that is where we'll get into kind of the economic portion with the cost loss analysis, and then just our final conclusion. So just an overall timeline, like Dr. Simmons was talking about, it started back in August 2018 with Allison creating that behavioral ranking scale and survey and using businessmen and women in the North DFW area to kind of solidify them. And then in March, she started sending them out, different chambers of commerce around the DFW area. In total, we had 403 different firms respond to the survey. However, when I started collecting the data in August 2019, only about 182 were usable. But when running the final analysis, because we had 4 probabilistic warnings and 1 deterministic, we had about 900 observations in the regression analysis. And then up until this point, we've been working on that regression analysis as well as this cost loss analysis. So this right here is just kind of some basic information from the firms of the survey. Again, you can see that 182 completed and 403 started. But the bottom 2 graphs really give just some basic information of firms. You can see the types of firms we got. The finance and insurance firms and business information were the top 2 kinds of firms besides other. Other just means these firms did not think that they fit into the categories that we provided. Position within the firm is who is your decision maker in the firm. Executive led the way with about 120, while then other, also, again, they do not fit in any one of our categories, was in second. The biggest portion of kind of the survey in this behavioral ranking scale is finding out firms' behavior when they're given a severe weather warning. This was given to them at each for the probabilistic warning scenarios and the deterministic warning. The big things to note before I really get into this is when firms were asked this question, they did not know that the actions they were selecting were on a scale and the scale was completely randomized. It gives us a big opportunity to kind of compare the different probabilistic warnings to each other, as well as the probabilistic to the deterministic warnings. We start at the 1, which is the most moderate, going up to the 10, which is the most extreme. 1 is going to be continue business as usual, no changes. 10, stop production line. However, depending on the type of firm, this 10 can vary depending on what their maximum or most extreme action would be. From this, the firm actions, we create what are called average actions. For each scenario, firms were asked to select up to 5 actions they would take. So we decided we took all 5 of the actions that they selected, added them, and divided it by the number of actions they selected. The next 5 graphs are kind of show what, on average, do firms do during these specific warning scenarios. And we'll notice that the peak of each scenario is going to shift over, and the average action is going to increase. However, the number 5 selection, which is a check more reputable weather sources, is going to always be the most selected action. So we're going to start at the 25% probabilistic warning. You can see we have an average action of about a 4, and you can see the 1, 2, and 4 all selected over 100 times, or 5 again, as I mentioned before, with almost 150, and we only see 11 selections at the most extreme stopping production line. We're going to see as we continue forward, this is going to shift over more towards the extreme side. And now when we move to 50%, you can see the shift immediately. We drop almost half in that first action going to 52, and we now see over 100 at that 7 mark, bringing our average action to 5.3, which is a little bit over a 1 increase in firms' average action from the 25 to 50% probabilistic warnings. We see a smaller jump going to only a 5.7 at that 75% probabilistic warning. But again, we see more firms taking that 8, 9, and 10 selection. We now have over 65 at anything a 6 or above in terms of their average actions. And finally, that 100% probabilistic warning, we see a jump to 6.6 from that 5.7 at 75%. And we see the 7, 9, and 10 all see over 100 actions selected. And that 25%, we only saw 11 selected at 10, and we saw over 100 at 1. And now at the 100% probabilistic warning, we're only seeing 18 firms selecting that 1 action. Now that we know the 4 probabilistic warnings, we also gave the deterministic warning to firms to figure out which probabilistic warning most closely relates to the current deterministic. And we found that the average action was about a 6.43, which most closely relates to that 100% probabilistic warning, which was a 6.6. And just like the 100% probabilistic warning, we can see that actions 7, 9, and 10 were all selected over 100 times, with 5 still leading the way. And this graph right here is just going to show us all 5 different warning scenarios, and we can see that as the probability increases, firms' actions are also increasing, as well as that deterministic warning lying very closely to that 100%, and it roughly is going to equate to about a 90% probabilistic warning. Now that we know on average what actions firms are taking, we wanted to understand why they're taking these certain actions. Is it just the new probabilistic warnings themselves that changes their actions, or are there other underlying factors? So what we did was we ran a regression analysis, and more specifically using a logit model. A logit model uses a binary dependent variable. And you can see at the bottom, again, we have our behavioral ranking scale, which we divided in half. A 1 is considered active and is anything above the 5. So anything above a 5.0, that's 6, 7, 8, 9, and 10 are all going to be considered an active action, where anything below the 5 is considered passive. When we started running the logit model, we had to adjust some of our variables. Both the probabilistic and deterministic warnings were converted to categorical variables along with the position of the decision maker. We also had information on the decision maker's experience, whether or not they were trained, and their false alarm experience, and those were all transitioned to binary. Binary meaning 1, they had experience, or they had training, or they had experienced false alarms. 0, they had not. As well as we have information on their customers that they see per day and the number of employees that they have per day. And this is just the overall results, and you can see here all of the warning scenarios are significant, which is great, meaning that these different warning scenarios are influencing firms' behavior. But besides the warnings themselves, we can see that trust in warning is the most significant variable, meaning how much they trust that specific warning is going to be very important when they're making their decision, as well as the trained decision maker. So being trained and making severe weather choices is significant, and the position of an executive and communication liaison. We can note real quick that both customer numbers and employee numbers have no significant effect. So really the size of the firm is not going to influence the action they're taking. But now that we have these results and we know that they're significant, we need to kind of understand why or how much they'll change firms' actions. So to do this, we create what are called point estimates to try to find the probability under a current scenario that the firms are going to take this active action or this passive action. Our baseline estimate is everything set to their mean value and categorical and binary variables set to the highest selected. Every binary variable was set to 0, as in the survey, that was the most selected. The position category, as we looked at earlier, executive was the most selected. The trust in warning, which was given at each specific warning scenario, was set to its mean value. And then we'll have 5 different graphs on this next slide, kind of showing when changes are made in these variables, how it influences the probability of firms taking an active action. So there is a lot on this slide right here, but just overall, the very middle graph shows when everything is set to that mean value, what is the probability at each specific warning firms are going to take this active action. The first 2 things to note, that having a trained decision maker or moving your decision maker from an executive to a communication liaison are both going to increase the probability of taking an active action. However, the biggest differences that are made here are the maximized and minimized trust. We can see that when firms have the highest trust level in a specific warning, this question was given from a 0 to a 10. So if they have a 10 on their trust, it greatly increases their probability of taking an active action, where we see almost above a 70% at the 50, 75, and 100% probabilistic warnings. However, when firms have no trust in the warning, the probability of them taking active action greatly decreases. So just kind of wrapping up this first portion of the survey, the descriptive stats, and the analysis, we see that firms are kind of prefer safety over that profit. The trust in warning is going to be very important when firms are making the decision. Who is the decision maker? Are they trained? Do they have experience? Those are important factors when firms are making decisions. That deterministic warning, again, lies roughly about a 90% probabilistic warning, which is going to be important going forward. And again, that size of the firm, how many customers they see per day and how many employees they see per day are not necessarily going to influence the certain actions they're taking. So next, we are going to get into this economic impact. This graph on the left is what we expect our cost to look like. The yellow is that deterministic running along the line. And then the gray is going to be the probabilistic warning. Again, you can see the deterministic and probabilistic cross right around that 90% threshold. And then on the right, we have are just different elements. So what I'm going to do over the next couple of slides is kind of give the brief overview and kind of the results from these different calculations. But after the conclusion slide, I have all the breakdown of the math, if there are any specific questions on how we came up with these certain elements. And basically, we're just trying to see if this new probabilistic warning system provides a savings compared to the current deterministic. So this is our basic equation. We're trying to find the expected warning cost. And the expected warning cost is made up of two equations, the expected response cost and expected preventable loss. And each of those are its own equation. The expected response cost is made up of the response rate. What percent of firms are taking this active action at this specific warning scenario, multiplied by our weighted average response cost, which was given in the survey, which we'll go over here in the next slide, but it's just how much does it cost your firm to take action. The expected preventable loss uses the non-response rate, so the percent of firms not taking action. What is the potential loss firms have? The probability of occurrence of that specific at that specific warning scenario, and the strike rate, which we'll talk about a little bit later. So the components of the weighted average response cost. This number right here is kind of the foundation of all of our other calculations. It was given from the survey responses. You can see on the left, firms had 4 different options for their response cost, and since we didn't have specific numbers, only ranges, we used 3 different weighted average response costs. We took the low end of each of the ranges, we took the midpoint, which we used throughout this presentation to illustrate, and then we took the high end of each of the ranges. This gave us 3 different weighted average response costs, so that way we could have 3 different estimated savings at the very end. Also, on the right side, you can see our survey data compared to national data. We were very much heavy on the bigger firms with over 16% of 100 plus, while nationally there's only about 5%. So we post-stratified the sample to reflect the national strata based on firm size. That way our survey, our economic impact results weren't necessarily biased towards our specific DFW region, but could be used on a more national level. So this right here is our expected response cost. It's that response rate times that weighted average response cost, which was about $13,000. And we can see that deterministic cost about roughly $10,000. And we can see at every level, except for that 100%, we are seeing a savings, and that at the 100%, we see a cost of about $500, where it's a little bit above at almost $11,000. As we can see, the greatest difference is at the 25%, that expected response cost is only about $2,500, again, compared to that deterministic of about $10,000. And we can see it's roughly monotonic, going from about $2,500 to $6,000 to $8,000 to that $10,000. So this is 1/2 of that expected warning cost. And next we have to calculate the expected preventable loss. And the components of that is that potential loss. So what is that weight? Then that's just made up of the weighted average response cost divided by that specific probability. The non-response rate, probability of occurrence for each probabilistic warning is just that specific warning probability. And for deterministic, we used 1 minus the false alarm rate. And then lastly, the strike rate, which is just the ratio of the average tornado footprint. And we actually expanded it because at first we did length times width, gives us about 0.33, but we tripled that just to account for that residual debris field to make sure we are accounting for everything. And in terms of the strike rate for the probabilistic warnings, we got about 0.5%, and for the deterministic warnings, we got about 1/3%. So now we look at our expected preventable loss. This graph is a little bit opposite of the expected response cost. We can see the deterministic expected preventable loss is about $4, where the probabilistic warning is about $21 at 25% and goes down to about $12 at 100%. The one thing to point out here is that at 75%, we do see a greater expected preventable loss than at 50%, which we can attribute to the response rate or change in response rate. There was about a 20% change, 25% change in firms that were taking action from that 25 to 50%, and about the same from 75 to 100, but we only see about a 10% increase from 50 to 75%. So firms are roughly viewing that 50 and 75% probabilistic warning the same. That, along with the potential loss being greater at 75%, leads to this a little bit higher expected preventable loss. So now we have both parts of the expected warning cost. So now we can put them together. And again, this looks very similar to the first graph we saw, and as well as the expected response cost. We can see that the deterministic again lies around that about $10,000, and only at that 100% are we seeing a cost. We're seeing the expected warning cost difference of almost $8,000 at the 25% level, $4,000 at 50, and about $2,000 at 75. Now that we have the information on the expected warning cost of the deterministic and each of the probabilistic, we need to see what are the potential savings at each of these specific warning scenarios. So this is our per firm per warning savings. So if a firm is given this specific 25% warning, they're going to see an estimated savings of around $2,000 compared to that deterministic warning, and it's going to slowly drop off as we go down, about $1,000 at 50% and $500 at 75%, and we see a small cost of about $120 at that 100%. So now that we have the per firm per warning savings, if a firm is, now we need to calculate what is it on an annual basis. How many firms are being affected, and using that along with our estimated savings, we can calculate the total annual savings. So to calculate the annual savings, we need to see how many warnings there are per year. What is the average square miles of a given warning, and how many firms are there in a per square mile? So we use the data from the top 21 tornado states to gather this information, and we found there's about 1.6 million firms that are affected every single year by a warning scenario. So this 1.6 million, along with the overall estimated savings when using all 4 of the warnings, about $3,000, we get this estimated annual savings of about $5.4 billion. And this is using that midpoint weighted average response cost that I was talking about earlier. But if you use our low point estimate, we're about $2.3 billion. And if you use the high point, you get up to almost $7.7 billion. So you can see we have a range of estimates here, but it's still, even at the low point, we're seeing a $2.3 billion savings. And if we want to get into the lifetime benefits, let's say a 2% discount rate going for almost 20 years, and using that midpoint estimate of $5.4 billion, it gives us that net present value of about $88 billion. However, we did have some limitations throughout this process. Using the ranges for that response cost kind of limited us in terms of having specific numbers. We did use the ranges, the low, medium, and high end, to kind of account for that, but having specific information on an exact number that it takes firms to respond could help even further this result. The firm distribution, again, we had a larger sample of firms with higher number of employees. Although we did do this for our economic impact, for actions that are taken by firms are going to be changed maybe by different sizes or who's in charge. So having a better sample of the firms, more representative of the national data, could improve our descriptive stats and just give us a better understanding. And lastly, just that we were only in really this DFW Metroplex area, so expanding out to further regions could help us gain even more information. Finally, just some conclusions. We see that the probabilistic warnings provide a great estimated savings compared to this deterministic warning. The National Weather Service can influence the decision making along with the decision maker, providing trainings and helping them have more experience in understanding these severe weather warnings, as well as improving the warning over time, giving firms more trust in the warning. And again, we're seeing that minimum savings of $2.3 billion. Going forward from this, getting that more comprehensive survey, gain more information about firms so we can really understand why they're taking these certain actions. Have the exact warning pictured that firms are going to be looking at would give us, combined with ours, could give us even more information on why firms may take specific actions. How much does what they're looking at really impact their decision making? Using more than just this one cost and loss analysis, give us more estimated savings, and just figure out exactly to even narrow in on a specific number. And then survey on individuals. Firms compared to individuals are going to act a lot different when given probabilistic warnings, and their motives behind their actions are going to be very different. Just overall, when firms are provided better information and trust the information increases, they're making cost-effective decisions, decreasing societal costs. And through this research, we have ended with 2 papers. The first paper going through the descriptive stats, the regression analysis, and the point estimates, and then the second paper which walks through this economic impact portion. And with that, I would like to thank you for listening to my presentation, and I welcome the floor to any questions or comments.
Great. Thanks so much, Seth, Kevin, and Kim. We do have a bunch of questions that we'll try our best to get through. And I'm going to start with ones that came pretty early on. So this first question is directed towards Kim. What sources will drive the new TWIEP products? Assume something other than radar, such as satellites, are used?
Oh, by this, I'm guessing that they're meaning the technologies. Yeah, so a lot of what's going on now is the observation systems are important insofar as they are able to also then drive modeling systems. So a lot of work is going on to generate the estimates of probability based on a couple different things. There's if we take climatologies, for example, of how storms that have different characteristics have behaved in the past. That's one way you can generate a probabilistic estimate, so something climatology driven. Or you can have a dynamic model that takes current environmental conditions and then creates a shorter term forecast. And it's a frontier that is being explored very heavily at my lab, NSSL, and others. If you're interested in learning more about that, I suggest that you check out some of the work under the Facets program and Born on Forecast program. Thank you.
Thank you. Okay, our next question. This one's open to anyone. Will you be able to capture the change in tornado emergency behavior preferences, especially in vulnerable populations due to the impacts of COVID-19?
I'll go ahead and just step in on that. I mean, Kevin and Seth, feel free to jump in if you'd like to. That's not something that we're explicitly testing for in this study. I will say I do have another quick response study going where that's something that we're looking at more explicitly, but just with the current warning system, certainly not with something comparing to a future system.
Great, thank you. Next question. Are there concerns that people will be less likely to respond to actual warnings? Have you studied the likelihood of a tornado hitting a point and how that relates to a probabilistic forecast of 25% for any given location?
Sorry, I feel bad, Kevin and Seth, but I know they're probably looking at me like, this is a Kim question. This is something that we are currently exploring. We're trying to actually figure out what's the best way to couple warnings with the probability information. There'd been some idea early on that perhaps warnings could fall out at a particular probability level. That's proven to be really complicated and problematic for a number of reasons, one of which is warnings, it turns out, to forecasters and to end users and the public, they don't just mean likelihood, they also mean things like vulnerability and impact, societal forcing functions, not just about the attributes of the hazard itself. So that's still work we're undertaking, but we are very interested in knowing that. If we were to give a warning but have a lower probability underneath it, what might happen. When we separate these two things out and we just look at if you're given one or the other, we are able to see that people are responding much like these businesses did. When the probabilities are lower, there's a propensity to take less protective action, which can be viewed a number of ways. I personally view it very favorably in that will those studies have also shown that individuals trust the information more. They can calibrate their own personal responses better to the information. So perspectives to be taken on that and more work to be done. But overall, the studies seem quite positive in that the outcomes, at least in experimental situations, are very good.
Thank you. Our next question. Why was the DFW area chosen for the survey? Were any other areas chosen?
I'll answer that one. That was simply a function of convenience. Austin College is located just north of the Dallas-Fort Worth area. And so it was one that we could easily get to the chambers of commerce in the DFW area. And so it was strictly one done for convenience and in the location of where our college is located.
Great, thank you. Next question. Was there an interaction between type of probabilistic warning and trust in warning?
Right. The interaction in the regression analysis, no, but so in the survey, each specific warning scenario they were given a question, how much do you trust this specific warning? So at the 25% probabilistic warning, they were to say how much they trusted the 25% warning, how much they trusted the 50% warning, and 75% going so forth. So we had information on how much they trusted each of the 5 different warning scenarios.
Great, thank you. Next question. Please explain why so many survey responses could not be used. Did they not answer all the questions, or were the category descriptions not relevant to a given business responder?
Yeah,
I'll try that. Oh, go ahead, Seth. Go ahead.
So there was a couple reasons. One, a lot of firms, maybe we had 403 that started and 102 used. So a lot of them didn't finish the whole survey. They would do maybe parts of it, or answer a couple questions here or there. So the 182 that were used in the regression analysis were survey or firms that answered every question in the survey that we used in the regression analysis. And the basic descriptive statistics that's in the first paper and that we use kind of throughout was any firm that answered that specific question that we were looking at. But the 182 just comes from the specific questions we were using in the regression analysis. Not every firm answered. So that's the major difference between the 182 and 403.
Great, thank you. Next question. This study focused on monetary costs, but was there any look at possible increases in injuries or deaths due to changes from deterministic to probabilistic warnings?
This is Kevin. No, we did not look at casualty rates, but that is a very interesting element that I think needs to be included in future research, because you can infer that if response goes up, that casualties will likely go down. And so I think that's something that needs to be looked at. But no, for this, we were strictly on the work that my students were doing, was looking at it on that financial arena.
Thank you. Next question. Does the response cost vary with warning lead time, or does the probabilistic value inherently include that?
We did not try. Kim, was that you?
Yeah, you can go ahead.
We did not try to explicitly discuss lead time. Implicitly, the warning that you would get for a 25% probability is going to allow more time than one at 75%. So there is an implicit inclusion of that, but explicitly we did not assign a warning lead time to each of the probabilities.
And this is a sort of tough question, because there could be cases where you get you have a 25% probability value, but you're actually quite close to the storm. So the quote unquote lead time would be low. I think it's a really interesting thing to try to grapple with decisions made over time. We were trying to get at, since what we were trying to get at was already so thorny, we'd made the simplification where we took out time as an explicit aspect of this, and we sort of forced them to make the choice based on the probability value. But in the real world, it could be that businesses make a succession of choices, or that time does weigh in. So I think that's a really interesting question and an important aspect of potential future work that could refine this sort of estimate.
Thank you, Kim. Our next question. Any insight on the firms that don't respond to the current deterministic warnings, but do appear to respond to the 100% probability?
Not specifically or off the top of my head. It would be maybe in the descriptive statistics. I think also just from with the further research, getting more information about the firms, because now that we know kind of what decisions they're making on specific warnings, we can maybe narrow with more questions that could give us information specifically on why they're taking those certain actions. But specifically between the 100% and deterministic, we don't know exactly why they're either taking the action, not taking the action at deterministic, but taking action at 100%.
Great, thank you. The next is sort of more of a comment, it seems, but if you would like to respond to it. You have used a very low discount rate, 2%. This means the future payments needed to be allocated will be very huge. OMB has recommended the lowest at 3% and the highest at 7%. This just seems like a very hard-hitting number.
I'll address that. This has really been a problem for doing this type of analysis with interest rates doing what they've done in the last few years with this dramatic drop in interest rates. We chose 2% because it's roughly three times the current 10-year Treasury rate. 10-year Treasury rate's running right about 0.7 or thereabouts. So that's why we chose that. But certainly if you increase the discount rate, that 88 billion that you saw as our estimate over 20 years would drop. But we simply wanted to use that as an illustration of what kinds of impacts you can get when you think not just about a year to year, but when you think about a longer time period.
Great, thank you, Kevin. Next question. Probabilities will change for users as storms evolve. How do you expect changing probabilities would impact these results here?
See earlier conversation about time. Yeah, while the storms would near a person and they might do different things as the storm nears, yeah, the probabilities are going to change also. There's only been a little bit of research, even just with any sample of the public, not just businesses, that's tried to grapple with choices as they evolve over time, as probabilities evolve over time. And actually something it's generally shown is that people may overweight the probability a little bit more as compared to a static rendering. So by that I mean, if you were to see like a 25% probability, they might respond one way when it's static, and they might actually be a little bit more inclined to respond when it's dynamic and moving toward them. So it's a very interesting question, and again, something that would be done best in a treatment that extends decisions from a single time decision to allowing for multiple kinds of decisions to unfold over time.
Great. Our next question. Which Lazo paper was used for your reference, noted as from 2017?
It's a training that he gave on different methods for doing sort of the non-market valuation, but for goods like this. And when he was looking specifically at products that offer probabilistic forecast information, that's what we were borrowing from.
Great, thank you. Next question. Do you feel it is possible to couple probabilities of a tornadic event with the maximum potential of that event? Moderate risk tornado, but if the tornadoes do form, they could potentially be EF4 or EF5.
Okay, sorry, I want to make sure I do. So this was a question about coupling like potential severity with this probability piece.
Yes. Mm-hmm.
That's another really great idea. That would be something that it would be, instead of just looking at this one single product, which the TWIEP has been interpreted to kind of focus a little bit on this 1 hour timescale because that language is so explicit. But the broader facets program, which is aiming to extend into, give more continuous information across different scales, also includes more probabilities, spanning into, say, the SPC timescale. So offering more environmental probabilities than just storm-based ones. So what you'd start to see then is that users would incur multiple layers of probabilistic information. And I would expect myself that if you had a day that had a background environmental probability that was higher, so that would be an SPC, a category, it would correspond to higher SPC category, that people might be more inclined to take these fee plumes, the ones that are the storm-based probabilities, a little bit more seriously. That's just a hypothesis, hasn't been done yet, but it would involve layering multiple layers of probabilistic information for the decision maker.
Great, thank you, Kim. Next question, does firm behavior match actual deterministic warning characteristics? I.e., does firm response to deterministic warning match response to equivalent probabilistic warning?
Well, I'll take this one. As Seth showed in his earlier, one of his earlier slides, our estimate of how the deterministic falls within this probabilistic range was pretty close to the 100%. It was right at about somewhere in the 90% range. So that was our attempt to try to overlay the deterministic to probabilistic, but that's as close as we can get to answering that question right now. Is that our estimate of looking at the actions that they take in a deterministic and compare that to probabilistic, where does it come the closest to? And so would somebody be there approaching that 100%?
Thank you, Kevin. Okay, our last question is a little bit more of a comment, and I hope the asker forgives me for adapting their comment. He's saying that the probability distribution within the warning polygon looked a little simplistic to me. Had the probabilities had more of a fan shape spread out and downstream from the storm's current location, that might also have affected the behavior some. Do you have any comment?
It may. We simply started with I guess as a simple place to begin, but that's actually we're testing that now, the effect of different trajectory representations with general public samples in the lab. So we'll have more information on that I would suspect would also translate to business decisions. But keep in mind the calculation that we've done that Seth highlighted, you know, that strike probability is sort of convolved with like how big is the space spanned by this product. So that at least is involved in the calculation here. If you were to have a wider plume, I think what you would see is our estimate drop a bit. Kevin and Seth, you can check me on that.
Well, we haven't looked at that, but if you had a larger area, that trying to adjust it for the probability of a particular location being struck would decrease the value of that potential loss.
Great, thank you, everyone. I am not seeing any more questions hop into our question panel. And so with that, I would like to close this webinar out. Thank you all for joining us. I hope everyone is staying safe and well, and I hope you all have a wonderful rest of your day. Thank you.